Okay, so we have seen the hash function, which is a function from set of universe of the keys to a given slots. So, suppose 0 to m minus 1 slot. So, it is a function from u2. So, you given a key, if we apply this hash function, it will be it will map to a particular slot. So, h of k is say I. Okay. So, now we say that we know a hash function is good hash function if there are say n keys, n is the k1, k2, kn and there are m slots. So, if the keys are distributed uniformly over this slot. So, n is the number of keys and m is the number of slots, then alpha is n by n, which is basically expected. Now, this is called load factor, which is basically expected number of keys per slot, and then we call this hash function is a good hash function because it is distributing the keys uniformly over the slot. So, now in this lecture we will construct few we will try to construct hash function and we will see whether this is a good hash function or bad hash function. So, let us talk about some example of hash function. So, how we can choose a hash function? Okay, so example of hash function. So, first one is the division method. Division method. So, here we are assuming our keys are basically integer. So, we have integers, all the keys are integer basically, and we have a slot of size m, which is also an integer. So, m minus 1, these are slots. So, we take an integer. So, we need to after applying the hash function, it should be one of these slots. So, m minus 1. So, what is the function we can use for that? What is the obvious function we can think of that? Modulus function, yes. So, that means h of k is basically k mod m, where k is an integer, m is also an integer. So, if you take the mod means if we divide this k by m, k is a key could be any big integer. Okay. So, any big integer we take and we try to divide this by m, and this is the remainder. This is the remainder, and this remainder will be from 0 to m minus 1. So, this is the hash function. Now, we will talk about how this hash function is. So, whether this is a good hash function or bad hash function. That means, whether it is distributing the keys uniformly over the over these slots, or there is huge number of collision for this. Okay. So, for that, so if our m is say some 2 to the power r, then we have a problem. What is that problem? So, if m is 2 to the power r, so then suppose we have a key say k, which is a integer, and we convert into binary say. So, suppose this is 1 0 1 1 0 0 0 1 1 1 0 1 1 0 1 0. Suppose this is our key. We have an integer, we convert into binary. We know how to convert into binary. We try we divide by 2 and then again 2 like this. So, we will get all this component. Okay. So, this is basically the binary representation of our integer. Now, suppose k is basically 2 to the power r, say r is 6 here say. So, for this r is say 6. So, m is basically 2 to the power 6. So, you have, if r is 6, then what is h of k? H of k is basically k mod m. So, 1 2 3 4 6. Okay. So, this is basically our h of k. If we choose r to be 2 to the power m to be 2 to the power r, I mean here r is 6, then this is basically h. So, it does not matter what are the values are. So, that means if we take any bit differ over here, so they all they are collating to the same. So, we fix this. Why this is happening? Because if you take mod of this, mod of 2 to the power r, then we take up to, so this is basically, we can just try to write this. So, this is basically if k is say k0 k1 dot 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 kl. Okay. So, this is basically k0 plus 2 k1 plus 2 k2, this is binary dot 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 2 to the power, sorry, 2 square 2 square k, yeah, 2 to the power l kl. Okay. So, now this can be written as k0 plus 2 k1 plus 2 square k2 plus 2 to the power r minus 1 k r minus 1 plus 2 to the power r, then we take the common here, then kr plus dot 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 like this. Now, if we take, if our m is 2 to the power r, now if we take this k mod 2 to the power r, then that means this portion will be vanished and only these values will come. So, that is why if r is 6, this is the k mod 2 to the power 6. Okay. Does not matter what are the values these are. Okay. So, if we change these values, any one of these values, by fixing these values, all are colliding into the single slot. So, there are huge number of collision is happening. So, it is not distributing uniformly over the slots. So, this choice of m is not a good choice. This is not a good hash function in that sense, if we choose m to be like this. So, usually for this we choose m to be prime, is a prime number which is not close to some 2 to the power r or 10 to the power r, because we may consider into the decimal system also. So, that is the choice of m one should be consider if we are having this division method. So, division method have this issue that we should not choose m to be 2 to the power r, then we have a huge number of collision. Okay, the second example is the multiplication method. So, there we are allowing m to be 2 to the power r. So, multiplication method, this is another example of hash function. Okay, so what we are doing here? So, basically we are here we are allowed to choose m to be 2 to the power r, and here we are, our numbers are say all are say w bits. So, our word are w bit word. So, our keys are w bit. So, our computer is w bit. So, 64 bit computer nowadays. So, 60w could be 64. Okay. So, now so our key is w bit. So, h of k is basically a into k will, so a is a constant again of w bit, we have to choose that a mod 2 to the power w, this is into, and then left right shift how many times, w minus r times, right shift w minus r times. So, where a is a w bit constant. So, if our computer is 64 bit, we choose a 64 bit constant a, and then we choose a key which is again a 64 bit, say w is 64 say, then we multiply these two, then it will be a 2 w bit. Now, we want to make it again w bit. So, that is why we take mod 2 to the power w. So, it will again become a w bit. So, the last w bit, and then we will do a right shift W minus R times. So, this is basically called the multiplication method. We will take an example for this. Suppose, so let us take an example of this. Okay, suppose say m is 8, 2 to the power 3. So, we have 8 slot 0 to 7, okay, and our W is say 7 bit. Suppose our computer is 7 bit computer, I mean old computer. Okay, so now we choose A is also 7 bit, we have to choose A, say A is a constant, we choose 1 0 0 1. So, this is our A say. Okay. Now, we choose a key which is also 7 bit, and we need to apply the hash function by this formula. Okay, so let us take a key. So, 1 1 0 1 0 1 1. So, this is our key say. So, now we apply this, we multiply this A into K. If we multiply this, this will be, this is 7, this is W bit, this is W bit, then the result will be 2 W bit. This is 7 bit, this is 7 bit. So, result will be 14 bit. So, if you do that, it will be like this 1 0 0 1 0 1 0, then 0 1 1 0 0 1 1. So, this is again 14 bit. Okay. Now, we have to take mod of 2 to the power W, mod of 2 to the power 7. So, this is up to 7 bit 1 2 3 4 5 6 7. So, this is the mod of 2 to the power W, and then we will do the right shift of W minus R times. W is 4, R is 3, W is 7, R is 3. So, 4 times. If we shift this 4 times, then what? Then this is gone, this is gone, this is gone. So, this is our basically H of K, this 3 bit. So, H of K is basically here 0 1 1. This is our H of K. So, this is the multiplication method, and here we are allowed to take M to be 2 to the power R. And this is and we have seen that, people have seen, this is sort of distributing the key uniformly over the slots. Okay, so one can have some more example of hash function, but this is the way we choose the hash. We have discussed two methods, one is division and another one is multiplication method. Okay, so now we will talk about a strategy to handle the collision which is called open addressing. We have seen a strategy for handling the collision, that was basically chaining. So, now we discuss another way we can handle the collision, open addressing. Okay. So, in the chaining what we did what? So, if we have these slots 0 to m minus 1, and if we have some keys, and if some keys are colliding in a slot, then we have a chain, say 75, 62. So, all this H of 52 is equal to I is equal to H of 75 is equal to H of 62. So, these are all the keys which are colliding into the, so 52, 75, 62. These are the keys, all are mapping to the same slot, ith slot. Okay. And then this is the collision, and we handle this collision by having a chain outside the table. So, this is a extra storage. So, we have to maintain a linked list outside the table. So, suppose this is not allowed, suppose no storage outside the table. Suppose this is our restriction. then we cannot do the chaining. This is chaining. So, if you are not allowed to do any extra storage outside the table, then we cannot have a linked list outside the table. So, the chaining cannot be applied there. So, no extra storage is available outside the table. So, everything we have to do in the table. So, we have a table or array of size m 0 to m minus 1, and everything we have to do there. Okay. So, that problem we have to address by open addressing. So, no extra storage. So, chaining is not allowed. For chaining, we need to have a linked list outside the storage, outside the table, but that is not allowed here. Okay. So, what is the idea? Idea is, so basically what we have? We have a table 0, 1, 2, m minus 1. So, we have a key, say we have key, so we are mapping over here. Okay. So, now suppose it is hitting to a empty slot, then there is no issue, but suppose it is hitting to a, so suppose this is say K10, suppose it is hitting to a slot which is already occupied, then what we have to do? We have to search for a next slot, because earlier method we have had a chain, but here chaining is not allowed, here no outside storage is available. So, linked list is not allowed in the outside the table. So, then we have to find a slot which is free. So, to find that slot, we cannot apply the same hash function. If we apply the same hash function, then it will again hit here. So, that means we have to apply a second hash function, and then again if that second hash function hitting some occupied slot, then we have to apply a third hash function. So, this is the probe sequence. So, we have to apply sequence of hash function or sequence of probing. So, we have probe sequence. So, basically here our hash function is for open addressing, it is basically a function from u cross 0 1 to m minus 1 to 0 1 to m minus 1. Okay. So, basically we first, so this is the probe sequence. So, we first 0th probe. So, we apply the 0th hash function. Okay. And suppose it is hitting to, so suppose it is hitting to some occupied slot over here. So, this is a K. So, suppose, so let us draw some example, it will be more clear. Suppose this is the scenario. Okay. So, somebody sitting here 5 1 2 6 1 1 say 7 1 1 like this. Okay. Suppose this is, these are the keys we have 5 7 1 1 6 1 1. Suppose now we have a key say 8 1 0. Oh, now suppose we want to insert 8 1 0 here. So, what we do? We apply the so we try for the 0th probe, we apply the hash function on 8 1 0. Suppose this is hitting here 0 1. Suppose this is hitting here. So, this is say 1, which is not empty slot. So, then we have to go for a next probe. So, this is basically the hash function which is giving us the value 1, which is not available, So, this is the first hash or original hash function maybe. Then we go for the next probe 8 1 0. This is basically h1 of 8 1 0, as if we have sequence of hash function. So, if we apply, because if we use the same hash function, it will hit here. So, we use, so suppose it is hitting some slot which is, so this is basically h of 8 1 0. So, this is h of 8 1 0 1. Suppose again it is hitting some occupied slot, then we have to go for the next probe. And suppose it is hitting some slot which is available. this is the 10 slot. Then we put 810 over here. Okay. So, this is the idea. So, we have basically sequence of hash functions. So, we have sequence of probe sequence. We first attempt the 0th probe or maybe our original hash function. If it is hitting to some occupied slot, then we have to, basically the idea is to search for a empty slot, okay, by this probe sequence. Then we will go for the next hash function or the first next probe, and if still hitting a some occupied slot, then we will go for the next probe like this. So, this is the way we insert the keys into the table, okay. And basically, so then our hash function is basically this U, so the set of universe of the key, and this is the probe sequence, and we will do up to m minus 1 times, and this is the slots available, this is the slot 0 to m minus 1. So, this is our function. Basically, we have sequence of hash function k0, k0, k1 like this. Okay. So, if one function is giving to some empty slot, some occupied slot, we use the second hash function with the hope that we will get a empty slot, and then until we continue like this, we continue this probing until we reach to a empty slot. Once we reach to a empty slot, we will put that. So, this is the way we insert a key. Okay. Now, how to search? So, searching is basically, so suppose we want to search say 810. So, what we do? So, suppose we are searching 810. So, what we do? So, we need to follow the same probe sequence as they have inserted. So, we first apply the 0th probe. So, it will hit here. So, we will see whether this value is 810 or not. It is not. So, we will go for the second probe. Then we will hit here. So, we will see whether this is 810 or not. It is not. Then we will go for the next probe. Then we will see it is 810. So, we got the value. Okay. So, this is the way we search. Now, deletion is little has to be tricky here, because suppose we delete this 611 suppose, and then after the deletion suppose we are searching 810, then what will happen? So, we will do this probe sequence up in the 0th probe, we will hit here. So, we check 512 is not matching with 810, then we will go for the next probe, it is hitting to a empty slot, then we stop, but this is not correct, because it is not originally empty, somebody was there, but it got deleted. So, that information has to kept somewhere here in a single bit, so that we can go further. Otherwise, if we see an empty slot, we will stop. So, deletion has to be in the deletion we have to take care this. So, if somebody if we delete somebody, then we have to put a tag over here that this room was not originally empty, somebody was sitting there and it got deleted. Otherwise, we cannot find 810. If we found this is empty, then we stop, but it is not the correct one. So, if we see this bit, it is 1, that means somebody was there, then we go for the next probe and we will found 810. So, deletion one has to be careful in the deletion. Okay. So, now this is the this is called open addressing. So, basically you have sequence of probes, and by there we will find the empty, we will try to find the empty slot in the table. Okay. Now, we will take some example of this probing. There basically we will talk about two examples. One is linear probing. So, two example of open addressing, linear probing. So, in the linear probing, the h of k comma I, so this is the ith probe, is basically h of k plus I mod m. Okay. So, this is the ith probe. So, this is very simple. I mean, basically if we, this is our slot, these are our slot m minus 1, 0 to m minus 1. So, suppose it is hitting some occupied slot, then this basically is looking the next one, whether next one is available or not. Okay. So, if it is available, we are putting there. So, this is because we have to everything we have to fix into the table, we are not allowed to have the chain. So, we just try to see the next one is available or not. This is the way we see whether next one is available or not. So, that means the 0th probe is basically our h of x, h of k. So, we go there, and if it is not available, then we go for the first probe. So, that means h of 1, this is basically h of k plus 1. So, we check suppose it is hitting the ith slot, then we check the I plus 1 slot is empty or not. So, like this. So, we have to take a mod because it may end, then we have to come back here. So, this is the linear probing, but this has a drawback because it is sort of clustering. If it is hitting somebody here and if this is empty, then it is basically clustering in some portion. Okay. So, clustering. So, it is not uniformly distributing the keys over the slots, it is sort of clustering. If it is hitting some occupied slot, then after that it is basically making a cluster, it is not distributing over this. So, to avoid that, there is another example of open addressing is called double probing. So, in double probing basically we use two hash function h1 and h2. So, in the ith probe is basically so h1k plus I h2k mod m. Okay. So, basically this is our table. So, in the 0th probe what we do? So, h of 0 is basically h1 of k. So, we say h is our original hash function. So, we apply the hash function. If it is hitting to some occupied slot, then we go for the next probe. Then it is basically h1k plus h2k. So, we have another hash function, we just add it and obviously mod m, check whether again hitting a occupied slot or empty slot or not. If it is not available, then we go for the next probe, which is basically h2 of h1 of k plus 2 of h2 of k. Okay. Since we have already calculated h1 h2, we can use this value to calculate this. We do not need to calculate again h1 h2 like this. So, we check this obviously mod m, we check this whether we are getting a occupied slot. So, this way depending on the if h1 and h2 are good hash function distributing, then this is shown to be a good hash function over the, I mean it's distribute the keys in the uniformly over the slot. Okay. So, this is slightly better than the double hashing, or one can think of it triple hashing or some quadratic hashing over here. So, in the next class we will analyze the open addressing method and we will see how good or how bad this is. Thank you.